Welcome, everyone. We're here for the May webinar. Thanks for coming. We're going to talk about basic HVAC. This is a great webinar for folks that are just starting out on their careers, or they just want to, maybe they've been working a long time, but they just want to expand their knowledge on HVAC and the basics and what you can do to save energy. We've got Andrew Vaillencourt. He's going to run us through all of this. Andrew has published a couple books on this, and they are written for normal people, not for engineers, or at least I think so. And although engineers will also like them, geez, let's just get going. So why don't you take it away?
Hi, everybody. Thanks, John. Nice lead off there. I am Andrew Vaillencourt, CEA, second generation energy auditor of some 22 years. I have written 2 books on this topic. I am the president and principal of SRG Energy Services, providing energy consulting, energy efficiency, project development, and a host of other energy-related services for ESCOs, municipal, institutional clients, pretty much all over the world at this point. We're pretty happy about that part. John asked me to come here. I love doing a lot of training. I do training for AEE. I do training for anyone who wants me to. And today we are going to talk about airside systems in HVAC, heating, ventilating, and air conditioning. To his point, I do like to keep these things at the basic functional level. I'm not going to ask you to do or understand any calculus today. There might be a smidge of algebra, but it won't be hard. And don't worry, I'm not going to quiz you. You will not be tested. All right. So without further ado, let's get into airside systems. That's me on the left. That's John on the right. So in any given building, you are going to transfer energy to and from places in and out of the building. And you're going to use media to do that. In this case, in an airside system, the heat transfer media is in fact air. That's why we call them airside. This is in juxtaposition or opposite of waterside systems, where we're going to pump water around. We're going to be digging into all the pieces and parts of a building that move air around in ways that make us feel comfortable, because that is literally the only reason to heat or cool a building, is so the people inside will be comfortable enough to do all of the things that generate profit for whoever owns the building. Air warmer, cooler, drier, wetter, or just having enough oxygen to not die. Turns out there's rules about that. So the truth, the building is just a box. Whenever we do these sessions, we did it for waterside, we're going to do it for this one. I need you to keep in mind that a building is just a box. It is a 6-sided vessel, and we pour things into the vessel, and hopefully profit comes out. Or if we're a non-profit, hopefully product comes out, or whatever it is we're trying to get out of the building. One of the things we pour into the building is energy. We put people in the building, we put supplies in the building, we put water in the building, we put food in the building, but one of the things we put in the building is energy. All of the energy that goes into the building will come out of it eventually. That's just a law of thermodynamics, and you cannot break those. So air is one of these resources. You have to put air in the building, you have to condition the air that goes into the building. Air serves 2 main purposes. We need it to breathe, and it is our energy transfer medium. All the energy that goes to the building is going to be used 3 ways: keeping the space safe and comfortable, and that is most of what we're going to talk about today. It will go into illuminating, that's lighting, don't worry about that, and it will go towards powering the various devices and widgets necessary to producing whatever it is we produce. That's process. Not going to talk about that today, although sometimes airside does play a role in process. What's important for every load, a system, all right, no matter what whatever load you're trying to meet, there is a system to meet it. Even if that system is just some firewood in the middle of the floor that you burn for heat, that is a system. And by the way, that is an airside system. All right. You got a lighting system, you've got an HVAC system, you've got whatever your system is for process, whatever your machines are. Each system is made up of devices. Your lighting's got luminaires, circuits, controls. Your HVAC system is going to have air handlers, pumps, controls, whatever. It's going to be made up of all these different parts, in your process, whatever. Got to move fast now. Every device has components. A system is made up of devices. Devices are made up of parts, of components. And you can keep going down this taxonomy till you get to the nuts and bolts and fasteners if you want to. The good news is we do not have to. We're going to get into airside now, okay? The basics. The basics of heating, hydronic is your water side. Why are we mentioning that here? Because they touch each other. Every air handler with a hot water coil, you have the water side touching the air side. They interact with each other. Very, very common to have air side and water side systems in a building. Some systems will only have one or the other, or some buildings, say we'll only have one or the other. That's actually fairly rare. You're going to have a hot air system for your heating. That's your air side. Okay. A furnace or burner is used to heat the air. If this furnace is inside a metal box on your roof or in a mechanical space and has a big fan to move that air, then it's part of an air handler, H&V, heating and ventilating, or makeup air unit. Those are your air side heating units. If it sits in the basement and only does a tiny area, then it may just be a furnace. Point of fact, people, this is a thing with me. People will talk about, oh, the furnace in their basement of their house. Odds are you do not have a furnace in the basement of your house. Odds are you have a boiler. Boilers heat liquid, furnaces heat air. Just a weird, or material. Believe it or not, a furnace can heat material as well. But if it's heating a liquid, it's a boiler. Just wanted to put that out there because people ask me for help all the time with their house. It's like, oh, the furnace in my basement is making a funny noise. Well, you don't have a furnace. And that doesn't help anyone, but it makes me feel better, and that's just the kind of guy I am. Then we got heat pumps. These can be air or water side, depending on the type of heat pump. Most of the heat pumps you see in the wild will actually be on the air side, as they're going to be direct expansion. Cooling, same sort of thing. You're going to have chilled water on the water side, but that chilled water coil is almost certainly, in almost every case, a chilled water coil will interact with an air side system. Hot water coils don't necessarily have to, because hot air moves on its own. It doesn't need a lot of encouragement to go where we want it to go. Cold air, however, is a little trickier to move around. You're gonna need a fan. Once you involve a fan, you have an air side system. More on that later. DX stands for direct expansion. That's the sort of air conditioning you're used to. If you've got one hanging out the window of your house, you have a DX air conditioner. All right, those will have a fan once again, because you have to move air. Anytime you move air, it's an air side system. Go ahead and jot that down, keep that in your head. Anytime air moves, you have an air side system, and it will have rules and devices and components. And then same note on heat pumps. Water source heat pumps will technically be water and air side. Carnot cycle, direct expansion, vapor cycle heat pumps will be pure air side. It's all about balance. Why are we doing this? The things we do inside a building, including just existing, are going to generate heat for the most part. Computers, copiers, screens, machines, all of it. These are your internal gains. You'll hear them mentioned as internal gains. Energy can be neither created nor destroyed. This is a law of the universe. You cannot break it. Do not break this law. You cannot break this law without breaking the universe. Please don't break the universe. We have no spares. Okay? Every watt, everything that goes into a building will become heat eventually. The electricity that comes in on the wires, that's lighting up my screen right now, before it's done, all of that power, all of that energy will become heat and have to be removed from the space before it cooks me alive. HVAC systems have one job. They exist for one reason and one reason only: to maintain equilibrium. We will talk about, oh, they heat, oh, they cool. Airside systems heat, airside systems cool. And that is not wrong, but what you really mean, and if you really want to sound technical, you're maintaining equilibrium. And your job as an HVAC system is to maintain equilibrium at a temperature and humidity that is comfortable for the people in the space or conducive to your process. I can maintain equilibrium at any temperature I want. I can save a lot of energy in a building by maintaining equilibrium at 42 degrees indoor temperature. I will make no friends. I will make very little profit, but I won't use a lot of heating energy. So the goal is not to heat or cool. The goal is to maintain equilibrium at a point that works for the site. That is the more accurate framing, and if you keep that in your head, all of this gets a lot easier to understand. Okay, your HVAC system, your airside system, is going to do this by adding or extracting energy from the air. That is the job of the airside system. It is going to add energy or extract energy from the air. When we add energy, it gets warmer. When we extract it, it gets cooler. All of it. They follow the thing for us as site operators or people working in the field is to remember they follow repeatable patterns. There are rules that lock these machines into repeatable patterns that once we understand, we can really, really do a good job of figuring out how the machines are running and how they might run better. And remember, the laws of thermodynamics are not just a good idea, they're the law. Here's a real short version, just take it with you. Energy enters the box through wires. It is used to do stuff like illuminate, cook food, and watch YouTube videos. Energy leaves the box through walls and windows if it's cold outside. If it's warm outside, energy moves from the outside in, because the second law of thermodynamics, and I'm going to paraphrase this really heavily, so if you're a physics major, don't come at me. Everyone's muted anyway, so you couldn't argue with me even if I was wrong. Second law of thermodynamics, energy always goes from high to low, period. Even if you think it's going the other way, it's not. Always from high to low, high pressure to low pressure, high temperature to low temperature, high enthalpy to low enthalpy. You cannot make it move the other direction, which sounds counterintuitive, but it's not. Different training. Airside, the parts. All right, waterside one training, we talked about how the pumps are the heart of every building. They move the fluid through the arteries that we call pipes. Well, if pumps are the heart, fans are the lungs. It moves all the air. Try moving air without a fan and tell me how it goes. Doesn't go great. All right. This is the workhorse of every airside system. There really aren't airside systems without fans. We are using air to move energy around the space, and the fan is what actually makes that air move. Now, you're going to encounter quite a few types of fans in the wild, and this is for the people who actually move around buildings, just so they understand. This big one you see over here, that's a very, very, very common HVAC fan. Probably 90% of the air handler fans, exhaust fans, and HVAC fans you find out there are going to look like this. This is called a centrifugal fan. It's called that because the air enters here, and centrifugal force forces it against the outside of this housing as this spins and throws the air out here in a manner we're going to discuss shortly. We like centrifugal fans because they follow something called the affinity laws, which we may or may not get into depending on time. They are also very, very efficient. It's probably, for HVAC purposes at low to medium static pressure, the most efficient way to move air, most mechanically efficient way to move air. Now, there are other ways to move air, and there's other reasons to do it that way. For instance, you see an axial fan right here. It's called that because the fan, the axis of the fan is in the airstream. These can get used, they get used all the time. People like these because they take up very little space and you can put them right in the duct. They are also not particularly efficient because they actually obstruct their own airflow. So you end up with with an issue of where they have to run at there's certain speeds where they run where their differential pressure across the blades is advantageous, and if they don't run at that speed, it's not advantageous. We don't like to have the blades of the fan actually obstruct the airstream, which is why a centrifugal fan is significantly more efficient. The air doesn't actually run into the back of a fan blade at any point in the centrifugal fan. Inline fans are just another kind of axial fan. Plenum fan is just any fan that you put inside a bigger box or a space above the ceiling without an air handler attached to it. And these will simply create negative pressure and move air out of the plenum. You have a jet fan. Jet fan is just a mechanical difference that we don't really need to go into. And an extract fan, which is the exhaust fan you see in every industrial garage in the world. We like that particular style of fan. It is a style of axial fan for those purposes, because these are extremely low static pressure environments and you don't need anything fancy to move the air. If there's no pressure to really overcome, and that's all an extract fan is doing, is just moving things out, then it's easy to just use this fan. It takes up very little space, uses very little energy. It also doesn't move the air very quickly. It doesn't move a lot of, it can move a lot of air under very low pressure. As pressure rises, its ability to move air falls off a cliff compared to a centrifugal fan. So extract fans are used, basically you stick them in the side of a wall, and when the exhaust alarm goes off in your garage, they come on, whoosh, and they very quickly move all the smoke and everything out. They do it cheaply, they do it easily, they do a perfectly good job for that, but they kind of stink for every other job. That's a lot on fans, but those are important. As you're walking around a facility looking at the fans you see in the wild, and you're seeing a lot of axial fans in your ductwork, you might wonder, is there a more efficient way to move that air? The answer is probably yes, and it's one of these. So the fan's job, how does a fan move air? It has one job, it creates a pressure differential. Ooh, big words, right? In the ducts that encourages air to move in the direction we want it to. The outlet of every fan is the high pressure side. The inlet is the low pressure side, right here. Can everyone see my mouse, or am I just gesturing at a screen? If you can't see my mouse, it's going around the outlet.
We see it.
Okay.
We see it. We see it.
This would be the high pressure side. If this was the only fan in the system, the highest pressure in the system would be right there. The lowest pressure in the system would be right here. When the pressure's high here and the low is here, everything in between, the air is going to move through to come all the way back around. That's all a fan does. It creates high pressure on one side, low pressure on another side. Okay, the air wants to move away from high pressure and towards low pressure. That's the second law of thermodynamics again, high to low. That's why I harp on this. The low pressure is at the inlet, the highest pressure will be at the outlet. When this is not the case, when the highest pressure in the system is not at the outlet of the fan, the air stops moving. If the lowest pressure in the system is not at the inlet of the fan, then the air will not return to the fan. It will go to wherever the low pressure is. Very important for my tin knockers, my sheet metal people, my ductwork people. It's probably the most important concept in their career. And that's why you'll get guys who went to trade school and maybe barely don't understand algebra, but they'll talk circles around you about pressure because that's their job and they know it better than anyone. Very important concept, because when the system breaks and everyone complains, that is going to be why. So let's talk about static pressure. Static pressure is the amount of pressure it takes for air to start moving. Static means to hold still, right? So that is the number at which the air stops holding still and starts to move. Okay? Ducts, dampers, filters, anything in the path of the air will increase the static pressure of the system. That number that you need to overcome to get the air to move. Every time the duct turns 90 degrees, every time you put in a filter, every time you put something in that ductwork, you're increasing the static pressure. The longer the ductwork, the higher the static pressure. That means you need a bigger fan, okay? If the static pressure of the system is higher than the static pressure of the fan, no air moves. And if that sounds basic, like, well, duh, of course not, the number of times this happens in systems in the real world will blow your mind. People add things to ductwork, people screw up their fans, they put in the wrong sensors, they put in the wrong motors, and no one can figure out why no one's getting any hot air. It's because the static pressure is higher than what the fan can overcome. And keep in mind, static pressure is the minimum number. There is dynamic pressure, or net positive pressure, which is what you need to have to get as much air as you want to move. So when I am 1 point above, so if my static pressure is 6 inches, if I produce 6.1 inches of pressure at my fan, my air's going to just start to crawl. If I want more air to move, I think we all know what I got to do. I got to produce 8 inches of static pressure. Now the air's moving because the static is 6, I'm producing 8. We get a lot of movement. If I produce 12 inches of pressure, that air's really gonna move because I'm now at twice that number. And there's a correct number of pressure, a correct quantity of pressure that will move the correct quantity of air through your system. And there is a whole lot of math that gets done to figure out how big a fan you need, how big an impeller, and what it takes to get the correct flow through your system. This math is complicated. These systems are complicated. When they're done wrong, you get starved air coils and people complaining and cats and dogs living together and all sorts of other chaos. Very, very important concept. If you need 6 inches of pressure for the air to move, that doesn't mean 6.1 inches is the right amount of pressure for your fan to produce, because very little air will move. Okay, we get into VFDs, that gets very, very important. Fan laws and fan curves, we're going to talk about those affinity laws. I'm not going to put you through it. This is a 0-0 level course. Here's the short version. The amount of energy a fan uses comes down to 2 things, pressure and flow. How much air do I need at the other end of my duct? Period. They're inextricably linked to each other by the fundamental laws of the universe. And in a centrifugal system, those are the affinity laws. You cannot change the pressure without changing the flow. It's impossible. They are inextricably linked, okay? The short version, moving a lot of air at low pressure is very, very easy. Your extract fan will do that. Moving the same amount of air at high pressure gets exponentially more difficult. It's a square. If I want to move twice as much air at the same pressure, I square the power I need to do it. Or I'm sorry, the pressure is squared based on twice the flow. Sorry, I had my affinity laws backwards. Ooh, faux pas, my father would kill me. Moving a little bit of air at high pressure is not so hard. So if the pressure is really high and I just want to move a little, it's still not that hard. Moving a lot of air at high pressure is exponentially more difficult, not linear, exponential. And the power rides these as a cube. So if I need to double my airflow, I have to square the pressure, and I'm going to cube how much energy it takes to do it. It goes up fast. That's the short version. This is why VFDs can save us more energy, but that's a completely different course. Key airside equipment focus. 99 times out of 100 in commercial buildings, we are going to be dealing with an air handler of some kind. What is an air handler? An air handler is a box with a fan and at least one coil. Some air handlers will have 3 fans. Some air handlers will have 24 fans. Some might have 5 coils. Some might have ducts going everywhere, whatever. One fan and one coil makes it an air handler. These are the usual parts. This is a fairly typical commercial, what they might call a packaged air handler. A packaged air handler is simply an air handler you bought with all the stuff you need already inside of it. All right, it's going to have an intake. It's got to take air from somewhere. If it takes all of its air from outside air, it's a ventilating unit or a makeup air unit. If it gets all of its air from the space with no outside air, it is a recirculating unit. If it does a little bit of both, it's just an air handler, because most of them will do a little bit of both. You have to bring in fresh air. It's a law. So you're going to have return air, outside air, and or both on every air handler. You're going to have a heating section and or a cooling section, because there's no reason to have this thing if you're not going to condition the air. You're going to have a filter, because that's the law. And of course, you're going to have a fan, often more than one. You'll see supply fan, return fan, exhaust fan on a big one is not all that uncommon. Lots of air handlers have just one fan to do all jobs. And if you've been paying attention, you know why. If this is where the fan is, this is the lowest pressure in the system. So it doesn't matter where I'm pulling from, because it all wants to go there. Remember, the air is always trying to get to the lowest pressure in the system. So this air handler works just fine with one fan, whether it's pulling return air or outside air. Makes no difference. It's just a question of which damper is open. However, in a lot of more sophisticated systems, they'll have a lot of fans just because it makes it easier to control exactly what goes where. Pedantic Poly says this air handler is constant volume, because the amount of air it moves will always be the same. Many AHUs you encounter in the wild will be variable volume, which means they can change the airflow to match. We're going to talk about that. 2 very important distinctions in the field. Those distinctions are very, very important when you think about how you're actually going to run a building. And this is just a cutaway. Everything about here is fairly typical. All right, so CAV versus VIV vis-a-vis the value of various versions. Alliteration is fun. CAV stands for constant air volume. It's going to send the same amount of air no matter what. And for about 90 years, this is what they all were. Willis de Havilland Carrier created the first functioning air handler way back in about 18 something or other. Until about 2002, they were all constant volume. We didn't start seeing variable volume really take over until the 21st century. There was a few of them. There was multi-zone units. There was some weird stuff that happened in the 70s, 80s, and 90s. But for the most part, it was constant air. And that's what you see on the left here. Here's your air handler. One supply pulls air from the space. Here's your return. It does whatever it's going to do. Maybe it exchanges with some outside air. Maybe it doesn't. And then it sends it right back out to the space. These are what they call discharge grills or registers. If you want to sound really nerdy, these are the registers. This air handler's fans will send X CFM. Let's call it 5,000 CFM. They can't send 4,500. They can't send 5,500. It will always be 5,000. That means the volume of air, whether they're using outside air or not, will always be the same. And there'll be a bunch of dampers, which is just vents, fins that open and close, to make sure that no matter whether you're bringing in outside air or return air, the total will always be 5,000 CFM. If you don't, you will break the fan motor. All right, they don't like when a fan motor is experiencing variations in pressure and flow when it's not designed to. They call that riding the curve, because every fan has a curve of how it performs at a given pressure and flow. And riding the curve is not necessarily bad unless you give it pressure and flow that doesn't sit on its curve, and then you will break the motor. Different training, higher level training. Just know that they're not supposed to ride the curve, and yet a lot of them will. On the right, we have variable air volume. And that means exactly what you think it does. It means we can change how much air the system moves, and we love these because fans use energy. This one is rated for 5,000 CFM, but all of these rooms are satisfied. They don't need any heating or cooling. All these little dampers close, and suddenly there's not a lot of air to move. This air handler, the one on the right, has the ability to say, we only need 1,500 CFM of air. I'm going to turn my fan down and only send 1,500 CFM of air instead of 5,000. We don't need 5,000. We don't want 5,000. So you're not getting 5,000. So that 3,500 CFM of air, you no longer have to move it. Now remember what I said earlier about the affinity loss. I've just reduced the airflow by 3/5, a lot, 65, 70%. If I apply the cube law, 0.6 cubed, that's where the 0.3, so I'm at about 1/8 the amount of power. I have saved 80% plus of the energy by turning that fan down, of the fan energy. On a 100 horsepower fan on top of a high rise, that is a huge savings. But it only works on a variable volume system. We talked about silver bullets. We talked about snake oil. The number of constant volume air handlers that were equipped with variable frequency drives in the 90s when the utilities were giving them away is embarrassing. One of two things happens when you put a VFD in a constant volume air system. It either doesn't do a darn thing or it breaks the system. Really the only two options. 90% of the time they just sit there and never change the speed. The VFD accomplishes nothing, savings are never met, and no one notices. Everyone high fives each other for putting in an energy saving device and they never look at it again. When I see a VFD on a constant volume air system, it's just, I just shake my head. The V stands for variation. But all through the 90s and early 2000s, when utilities were giving VFDs away, constant volume air handlers were getting VFDs installed, they were getting put on, the sensors were put on, the contractors were making money, the utility was able to show that they were spending customer money on these energy saving devices, and they didn't do a darn thing. And nobody is ever happy when I bring that up. So let's talk about how the airside system touches the waterside system, okay? This is a standard sequence of actions, all right? This is Joan. Joan is a real person. This is a stock image of a woman who is not Joan. Joan actually existed. She worked for the Moore Company in Westerly, Rhode Island, way back in the 80s when my father was there trying to save energy in textiles. Joan was always cold. Joan worked in accounting. She was in her 60s or 70s, and she was always cold. And that way, in all the trainings, whenever my father talks about it, it's like there's always a Joan. Every building has a Joan. Joan is never happy with the temperature. Joan is cold. She turns her thermostat up. She turns it up to something ludicrous. That thermostat, boom, it's going to send a signal to an air handler. Here's our air handler up here. The air handler immediately starts the supply fan right here and open the valve on the hot water coil. Now your water side and your air side have interacted. Hot water flows through the coil. The fan is going to blow air across the coil. Oh, here's our supply fan over here, sorry. So it's pulling air through your filters, through your hot water coil. The air now acquires energy from the hot water coil. Energy always goes from high to low. The air is now warm. The air is now 90 degrees. The fan moves this hot air through the ducts and towards the zone asking for heat. As the heat leaves the coil, the water inside gets cooler. Sensor tells the hot water pump to send more hot water, kicks on the boiler, blah, blah, blah. The hot air hits the zone, warming everything in it because it has more energy than the stuff it hits. Second law of thermodynamics. When enough energy is dumped into the space to hold the temperature at Joan's preferred 80 degrees, the thermostat tells the AHU it can stop sending hot air. All right. Energy immediately begins to leave. Once it's not adding energy, energy begins to leave again through all the mechanisms we talked about earlier. If left at 80, the thermostat will again signal for more heat as soon as the space cools off. At least Joan is happy. And the ending of the Joan story goes like this. My father had a Honeywell dial thermostat circa 1980 installed right above Joan's desk. so she could set her temperature whatever you like. That thermostat was not attached to anything. He screwed the plastic to the wall, not connected to anything. Complaints ceased. Joan never complained again because she had her own thermostat that she could manipulate. My friend and a guy I trained in this industry named Patrick Hagan, working for QJM, recently audited the Moore Company in Westerly, Rhode Island. 40 years later, the thermostat is still there, a true story. I wanted him to take a picture, he forgot. That Honeywell dial thermostat is still there in accounting above Joan's desk. Joan is dead, so we can say anything we like about her. But it's still there. He sent a picture to my dad, it was hilarious. Ventilation, it's the law. I'm not going to spend a lot of time on this because I think I'm supposed to be wrapping up. First, people will die of carbon dioxide poisoning if you don't give them fresh air. We have rules about that. Your Airside system must provide code fresh air. Code is determined by ASHRAE 62.1. Look it up if you like. Also, off odors will migrate around. My favorite example is when you go to the grocery store. Do you smell the fish department? No, you don't, because they move a lot of air through the fish department, so you don't smell it. The bakery, on the other hand, you'll smell right away. All of that's intentional, people. That's manipulating your Airside system. That grocery store probably handles 500 to 1,000 pounds of raw dead fish every day, and you never smell it. Think of the last time someone put fish in the office microwave and what that smell did. That's an Airside system not doing its job, just to give you an idea of why they're important. Never forget, outside air is expensive air. It has to be conditioned, heated, cooled, dehumidified, or humidified. We want to use the correct amount and not a drop more. And then COVID caused everyone to turn all of their ventilation way up. And then I will tell you, they've all forgotten to turn it down again. So if you're doing energy efficiency stuff, go ahead and check the ventilation rates. Most of them are still up there. All right, so here's a story. This is a real story. This is a thing I discovered, a thing I got to work with a few years back. There's an air handler on top of a laboratory facility, a research and development facility for a hydrogen fuel cell, hydrogen power startup. And they couldn't figure out why their electric bill was absolutely insane, which I found hilarious. They do electrolysis there. I'm like, of course it's insane. But it was actually too insane for what they were doing. So I data logged their giant air handlers and found that each one was using about 9,000 kilowatt hours a week in the summertime. 9 megawatt hours a week. Pausing, I'm saying that dramatically. If you don't understand exactly how much juice that is, I assure you, it's a lot. In late September, when I got there, I clamped some data loggers on, some hobo data loggers to watch how the air handlers were using energy, and the results were fascinating. So we have basically, I think this is a 36-hour period. I forget exactly. It's a makeup air unit, so it's 100% outside air. It runs fully loaded until 5:30 p.m. Absolutely no fluctuation. It runs flat out. And then at 5:30, it falls off a cliff. Now, if you know your air handlers, you know, oh, that looks like 2 stages of cooling shut off. And you'd be right. You can see down here, it drops all the way to about 100 amps. And then it starts. This is just cycling. This is just a compressor kicking on, kicking off, kicking on, kicking off. And I really hate seeing those short little spikes, although they're longer than they look. And then loaded and actively cooling through 9 o'clock. It gets a little bit late and it drops down to this level. This is just the fans and basic, but you can see the compressors cycle on and off, on and off. We don't hit a base load pattern or even shut off until the wee hours of the morning. Ladies and gentlemen of the jury, why is this thing running at all 2 in the morning? The building was empty. Nothing was going on. But it was running, big fans running, big air handler. We start to see morning warm up about 5. It goes right to first and second stage. Just kicks right on. You can see all 3 stages clearly kicking on, almost on a schedule, but it followed outside air temperature pretty well. And then by 10 o'clock, fully loaded by 8 a.m., and it doesn't twitch until 6 p.m. Fully loaded, no questions, running as hard as it can. And then as the evening comes, it starts cycling between stage 1 and 2 and never actually settles into a low load state. Overnight, this particular location, it was Eastern Massachusetts, it was getting into the 50s overnight. And this is a 100% outside air unit. There was no need to cool anything. They could have been using outside air to cool. They could have been economizing. But for whatever reason, this unit was absolutely flogged all the time. The result, the reality is that there was 3 separate building systems that failed in order to make this ludicrous graph happen in about $10,000 a month. Multiple airside systems were competing. They had electric reheats that were stuck in the on position, returning air way too hot. The laboratory hood VFDs were all running incorrectly. The boiler system had the wrong reset numbers. And I forget what the last condition was on this one, but it was a condition where the entire airside system was being told it was loaded for all hours, and it was costing tens of thousands of dollars. And it was all controls, by the way. There was no real expensive fix. The controls contractor, how he kept his job, I do not know, was able to come in and get all this and get it running following load. But this is an example of what happens in an airside system when you're not giving it the right information. 90% of the ECMs I discover when I walk a building in 2026 are controls related. Our buildings are in good shape mechanically for the most part. Most of what I'm finding is stuff like you see here. It's on airside, and it has to do with the fact that our airside systems tend to run fully loaded all the time. They run full CFM, they run full pressure, and they run full outside air or maximum outside air, whatever they're allowing. And that is driving energy costs through the roof. And it's usually a controls fix. It's usually not expensive if you know what you're looking at. This is just an example of what that looked like. And if you data log and if you do a good job watching your system, you'll see this happen in real time. So that is my story. I'll pause for questions. There, we made it. Good. Thank you, SRG. Thanks you. And at this point, questions, comments, recriminations.
Yeah. Well, here's the first one. Can you name your energy company again?
SRG Energy Services.
SRG. What's SRG stand for?
The Slide Rule Group.
Oh, of course. Of course. Of course.
I needed a name no one else had.
All right. Okay. Mike, a while back, I think he was talking. When you were talking about fans, he was talking about medium, or you mentioned low to medium static pressure.
Yep.
What was it that required medium to low static pressure, and can you define what that range is?
Oh, what a great question. So, low, medium, high static pressure is always relative. What is low static pressure in one system might be high in another. It's relative to the size of the fan. So there is no numerical number for that.
Yeah.
In most HVAC systems, in a, let's call it 100,000 square foot Class A commercial and office building, your air handler is probably running 1 to 2 inches of static pressure. That would be average.
Yeah.
I've seen them much higher though. I've seen 12-inch static in a hospital system. So.
Okay. Okay, so I've got a question. You mentioned, so let's talk ECMs. The typical ECMs you said they were controls related. Can you go into more details for some folks who want to know what to look for when they're looking at air handlers and how to save energy?
In the airside systems, there are 3 things that are killing energy in most of the buildings I'm looking at. One is outside air fraction. I don't know if it's COVID, I don't know if it's neglect, I don't know if it's apathy, but we are bringing in outside air all the time in massive quantities.
Mm-hmm.
Outside air is expensive air. It takes a lot of energy to condition it. There's a right amount to use, there's a correct amount to use. ASHRAE tells us what the correct amount to use in. And it's not one of those situations where if a little is good, more is better. There's no actual improvement in air quality going from the ASHRAE standard for whatever it is you're doing to twice that. The human nose, the human lungs will not tell the difference. The ASHRAE standards are already very generous with outside air. And they do that on purpose. They want people to have fresh air. ASHRAE doesn't get paid to choke people. The standards they set are, for instance, they talk about CO2. The CO2 threshold is 1,000 parts per million. I tell you right now, a human being, that's the point where a human being might actually notice. And a lot of places are running 600 parts per million CO2 before their demand control systems kick on. That's good for nothing. really, to be honest. The human respiratory system cannot tell the difference between 450, 420, which is what fresh air is, and 600. There's no discernible difference other than the amount of energy it takes.
So when you're doing energy audits, generally what I found is if any building that has 10 air handlers or more, there's at least 2 economizers that are screwed up. It's just that it's the easiest thing. It's like they're always screwed up. Yeah, 4 might be a better.
2 are straight broken and don't work. The rest are out of commission or uncalibrated.
And there are like 6 or 10 different ways they can be broken.
Yes.
But one thing I heard one guy say in a webinar or seminar once was that he said, you know what, economizers is a brilliant idea, but the fact that they're always broken, they probably in general have wasted more energy than if we didn't have them in the first place.
I think that depends on the year in question. In 2003, I probably would have agreed with that. They get better. Buildings are more modern. When I started out, it wasn't weird for me to go into a building that's 100 years old and hadn't been updated since the 70s. There's less of those. The buildings have been updated. You are right to point out, and it is right to point out, that economizers almost, if your building operators, your site operators are not on their equipment, they are not checking a lot, they get out of commission very quickly because they involve a lot of sensors. You need a return air sensor, you need a supply air sensor, you need an outdoor air sensor. And to do economizer, the most effective version being dual entity economizer. Oh, where's it going? We don't want to see the chats. Requires a lot of sensing and a lot of controls logic, and those are the first things that go. They're sensitive.
Okay, so here's some more questions from some of the folks. Let's see, we got a whole bunch now all of a sudden. So what are your recommendations regarding maintenance? How often? What should you check? Oh my gosh, now that's not a 1-minute answer.
Minimum in my world, if you put a gun to my head, if I'm running a building, actually, if you buy my book, there's a whole schedule.
That's right. That's right.
Checklists. But that being said, for something like for sensors, all of my sensing equipment, water sensor, air sensor, all of that, twice a year, just check and make sure it's not giving a dumb reading.
Yeah.
At a minimum. Hey, this says my water's 180. Is it? Yeah, it's 178.8. Close enough. Get on with your life. Twice a year.
Okay, next question. What are the best practices for managing outside air in hospital applications?
Ooh, they have a completely different set of rules. Don't do what every hospital I walk into does, which is just bring in all the outside air all the time so you don't get
Yeah, okay.
I just walked Connecticut Children's Hospital. We're going to save them 35% on their gas bill because all they do is dump outside air. It's all they do. They just 24/7. Best practice: commission your air handlers. Different parts of the hospital will have different requirements for air change. Now,
that's right.
Air change does not mean fresh air. That is a mistake every hospital operating room I go into has. There's rules for how many times you have to change the air. Operators think that means change with outside air. That is not the rule. The air has to go through a filter a certain number of times. Absolutely. And there has to be a certain amount of outside air. Absolutely. Hospital operators are confused on that. It's got to be 20 air changes an hour, as I think the rule, which is a ludicrous amount. Absolutely ludicrous. And these guys are trying to force 20 fresh air changes an hour. No, it has to go through the filter 20 times. I forget what the fresh air requirement is, which is still very, very high, but it ain't 20 an hour.
Yeah, yeah. So different. It's the different areas of the hospital have different air changes per hour requirements, and then different ventilation requirements, like surgery or the tuberculosis ward.
Yep.
Okay, that's one thing. But the records office, the pharmacy, maybe a little different. So
35% of every hospital square footage is admin, and that's 62.1. You don't have to do any silly hospital stuff in that. Commission those air handlers.
Yeah, so there's stuff in that. Where do you find those air changes per hour, the ventilation requirements? Is it that's in ASHRAE 62.1? Is that where it is?
ASHRAE will have some of them, and then there's a hospital rules addendum. I don't know if it's ASHRAE or not.
Or you could just ask AI. I'm sure they'll get it right, like 90%.
Yeah, someone asked Claude.
Um,
I was just working with this. I should know it because I was just doing the Children's Hospital in Connecticut, but I don't remember off the top of my head.
Okay, here's one. In many urban areas, outside air is often polluted. How do we bring in the fresh air in such situations? Do we just need better filters?
There are filtration requirements. If your filtration is up to code, it'll work. Or at least it's supposed to. If your filtration is up to code and your air still feels grimy, someone else is polluting your air and call the EPA on them. There's a discharge too close to what, because I have that happen. Like, why does my air smell like exhaust? And then you find out that someone, the construction yard the next door put 4 generators for their equipment right in front of your intake.
Yeah,
The filters aren't sized for that. They're not.
I was dealing with a building in Saudi where in Riyadh, I think, where they had the exhaust from some restaurant was going right into the intake for the rest of the building.
Yeah, your filters, if your filters are up to code and no one is discharging directly in, your pollutants should be under control. That's a filtration thing. If this person, if you were specifically having that problem, I would look at where your intakes are and what's near them.
Okay, here's something Michael said. ASHRAE 170 is the typical standard for medical spaces in a hospital.
Good.
ASHRAE 170. Okay, we got that answered.
Yeah.
Can you tell us about turning CFM to 0 overnight versus maintaining some minimal recirculation airflow? Oh, that's a good question. Because of humidity issues. So let me see. There's a little more of this question. Oh, does pressure buildup in the ductwork cause issues? I don't
Yes.
know how that works. So,
You can blow your ducts right out. You can blow your duct seals out. Happens all the time.
Wait, explain this. So you turn your air handlers off and then you just turn them on and then that.
Oh no, yeah. If you overpressure, I thought if you overpressurize your ducts because one of your sensors is wrong, a thing that happens all the time is a differential pressure sensor on a fan for the VFD. Bad reading for the VFD goes berserk, overpressurizes the ductwork, and you'll know when it happens because it sounds like thunder. Boom, boom, boom. And then over time, all of your duct seals will get blown out.
Okay, I got someone else making sounds. All right. Okay, so here's another
You
one.
want to talk about the overnight CFM thing?
Yeah.
This is pretty easy. If your building is dry, when everyone leaves, you've conditioned the air, it's dry, you can turn off the outside air and just keep circulating dry air. If that air somehow gets moist, you have a moisture problem, not an air handling problem.
That's right. And that means you can't be turning them off. So if you're in Alabama, it's probably a bad idea to turn your air handlers off.
Depends on how well your building's sealed. If the air inside your building is dry and you stop bringing in humid air,
right,
stay dry. If that air is somehow accumulating enough moisture overnight to be a problem, you have a moisture problem, not an air handling problem.
That's good. That's good. Here's one. Andrew lost me with his comment on CAV or constant volume with VFDs. We've been optimizing air delivery for occupancy, shifting load for years. In a VAV system, we do airside optimization by regulating static air pressure, supply static air pressure.
Yep, that's how you do it. That is correct. Now, on the CAV, I will speak to the CAV thing because I don't want to lose anyone on this.
Yeah.
There is a thing you can do on a constant volume system with a VFD. You can do a static pressure setback. When you do it, you are moving the system out of the flow and pressure it was designed for. That doesn't always break stuff, but you are moving it out of design. If the system was designed for different flow and different pressure, then it's a variable air volume system. So when we take an old CAV and slap a VFD on it, overnight, we can take that, we can limit. One of the things we used to do in the early 2000s is limit that overnight fan speed to 50 or 60%, half the flow, quarter the static pressure, and get some savings. What we were doing was starving zones, though. Now, no one was in the building, so no one cared. It's a form of setback. Now, just because you did it doesn't mean you've broken something. And you can get savings that way. Static pressure setback was a thing, and sometimes you can absolutely get away with it. If there is a lot of redundancy, a lot of lash in your system, you may find that you can run your fan at 85% and everyone still gets adequate flow, and there's savings there. That's not a VFD solution. That's an air balancing solution. You're using the VFD to balance In the Northeast, they will not give you a rebate for a VFD to do that. So it is right. I will, to that person's point, yes, you can do it. You can get savings, and you can do it without breaking the building. It is generally not what they're for, but yes, that is a completely viable point.
Okay. Any ECMs regarding mixed air set points and how they may be adjusted throughout the year?
Yes, this comes up all the time. Discharge air set point or mixed air set point. Honestly, you can fiddle with one, you can fiddle with the other. What you want to make sure is the air going out to your terminal units, your VAV boxes or whatever, is as close to the temperature you need it as possible so the reheat doesn't come on. Most reheats are electrical because running water throughout buildings is expensive. So if you send low discharge air temperature at the air handler because your mixed air temperature is off or your supply air temperature is off for whatever reason, those reheats are going to want to come on to bring that air temperature up. If they're electric, if you're heating with gas at the air handler and your reheats are electric, the reheats cost about 5 times as much per BTU, because the fuel is expensive, electricity is expensive. So the goal is to use those electric reheats for just trim, just a couple spaces. The worst case scenario is you cool the air down too much in the summer, and now you've got heating and cooling fighting each other. You're sending, Jones' office wants 55-degree discharge air, but the rest of the building wants 70-degree discharge air, and then Jones' office drives everybody's reheats through the roof. This happened at a building in Chicago recently where one conference room needed cold air year round because it was centrally located and not well ventilated. And so the entire 90,000 square foot site was getting 55-degree discharge air in the dead of a Chicago winter. And every electric reheat was running, and it was costing them tens of thousands of dollars.
Okay. Are you a fan of dynamic reset on outside air systems? And also, what's been your experience with airside economizers, especially in humid places?
Okay, great stuff. Dynamic setback, fancy way of saying that it's always recalculating the correct amount. If you have the systems and the personnel sophisticated enough to keep an eye on it, you're going to save a ton of energy. If you don't have either of those two things, you are going to save zero energy. That has been my experience. I use this analogy all the time. The F-22 Raptor is the most sophisticated fighter aircraft mankind has ever produced. The thing is a marvel of engineering. If you put me in the cockpit, it is going to crash every time. I don't know how to fly an F-22 Raptor. It doesn't matter that it's brilliant. It doesn't matter that it's amazing. It doesn't matter all the cool things it can do. I can't make the aircraft do them, so it's wasted on me. Sophisticated control systems. I did this training for the AEE. I did a whole thing on this. We are selling control systems and technology to people who are not sophisticated enough to use it the way it's meant to use, and that is not an indictment of the people. It is not an indictment of the people in the space. Some of the things we can do with technology are so sophisticated, you almost need to be a specialist to run them. Fully dynamic, fully integrated dynamic setbacks in any system require a lot of oversight, and they require someone who really knows what's going on in the building. When you have that, yes, your savings are going to be fantastic. Airside economizer, what they're referring to is sometimes called dry bulb economizer, is better than no economizer at all, as my grandmother would say. Usually referring to bad whiskey. Well, it's better than no whiskey at all. Airside dry bulb economizer, if that's all you got, there are savings to be made there. Someone needs to keep an eye on the relative humidity. You need a relative humidity lockout. So even if the air is cold but very, very humid, you don't want to use it. Or if you have airside economizer, if you have a dry bulb economizer, it's not a lot of money or effort to convert it to dual enthalpy. A couple of new sensors, a little bit of controls logic, it's the same damper, so just convert to dual enthalpy. There'll be savings there, and it shouldn't be a huge financial leap. And if it is, call me, I'll find someone to do it cheaper.
Okay, this is interesting. Air quality is a common problem with plumbing vents that are too short into roofs with parapet walls. The dead air gets sucked into the air handler.
Ooh, great one. There's a lot of building science in that question. This kind of goes back to the pollutant one we got earlier. If we are going to allow pollutants to collect near our intakes, we are going to have a problem. That's a construction problem. That's a plumbing problem, right? If that's happening, call your plumber. I say that as if I have any control, and your finance department says, no, we're not calling the plumber, make it work. That's a whole pet peeve of mine where the finance department says you can't have any of the things you need to do your job right, and then someone complains because you didn't do your job right. That's not a problem I can fix on this seminar. That is a problem that we have a lot. But you know, if the problem is that you have a contaminant collecting at your intakes, that's the problem. There's nothing I can do to your air handler that's going to fix that.
Okay, I think might be my last one I'm going to ask. Are there risks in terms of literally blowing ducts open or something like that in adjusting maximum cooling and heating CFM where sensible? That is, if max cooling and max heating CFM are the same, I might reduce max heating CFM as the faster the air moves, the more heat it loses. What are the system-wide risks of making small adjustments like these?
That is an exercise in tripping over dollars to pick up pennies. The faster the air moves, the more heat it gets. Now we're getting into Reynolds. I said there would be no calculus in this seminar, people. Don't make a liar out of me. In practice, that just doesn't come up. There's not enough juice in that particular lemon to be worth squeezing it. And there always is a risk of blowing out your ducts. Your ducts are rated for a certain amount of static pressure. You don't see it in smaller buildings, but if you're in a high rise, a 40-story mid-rise, it's going to have a very, very big air handling system. They might have a 200 horsepower fan somewhere, and a 200 horsepower fan will absolutely blow a duct out. And it's really, really interesting when it happens because it sounds like thunder. Ba-boom, ba-boom, you know, and it's like, whoa.
Yeah, you mentioned that before.
Yeah.
Okay, here's a last question. I looked you up online. I was, someone asked for your links to your books, and I found there's like, what you've written, is that you or someone with your name that's written all these science fiction books? Is it science fiction?
That is also me. I like to separate my hobbies from my work, but yes, I have about 17 science fiction novels as well.
That is crazy. How long does it take to write a book?
100,000 word science fiction story takes me about 3 months to write, another month to edit. Yeah.
Crazy.
That's
crazy. That's good for you, man.
I didn't find my cage fighting pictures though.
No, I didn't. I did not.
Those are out there somewhere. Those are old.
Okay, so now about these books, which is the best one? If we're going to try to read one of your science fiction books, which would be
one of my science fiction books?
Yeah, it would be the best one to read.
If
you wanted someone to be hooked on your writing and think, oh, I got to read all this stuff, what would be the book they should read?
If they have to like pulpy science fiction, but probably Sullivan's Run.
Sullivan's Run. I'm gonna check it out. All right, I'll write that down.
My favorite story I've written is Dead Man Dreaming, but that's in the middle of a series, so you'd have to kind of read up to it.
No, we're not gonna do that. Okay, Sullivan's Run. I'll check it out. Okay, I think we ran out of questions. Andrew, that was really good. I really appreciate you coming on.
I hope people got a lot out of it.
Yeah. All right, guys. Thanks for coming. We'll see you next month.
See you.